Welcome to all. Myself, Dr. Santosh Singh, working as an Associate Professor in Department of Physics, Institute of Aeronautical Engineering. In last video lecture, we were discussing about semiconductor optoelectronics courses, and in that we already discussed about EK diagram. Now, in today video lecture, we are going for discussion about importance of that EK diagram. So, what we get in last video lecture, we solved Schrodinger equation for actual crystal lattice or for practical crystal lattice, and we take one assumption that is given by F. Bloch. What he suggested? He suggested that the electron wave function in periodic lattice, this is your periodicity, electron wave function in periodic lattice will be in the form of this. So when we solve this Schrodinger equation, when we put this wave function in Schrodinger equation, this is your Schrodinger equation. So when we put this Schrodinger equation here, what we get? We saw that the energy eigenvalue also show the periodicity in nature and show some periodicity in K wave vector. Okay. So that thing already discussed in last video lecture. So when we plot this obtained energy eigenvalue and means energy eigenvalue and K vector plot, what we get? We get a picture like this. Okay. So what is this? This is your allowed energy eigenstates for n atoms arrangement in one dimensional periodic arrangement. In one dimensional periodic arrangement, if n atom will be arranged in one dimensional periodic arrangement, then this is the case where all this curve is showing your obtained energy eigenvalues for each allowed energy states. Okay, means see here, this is your first case, this thing. Okay, this is your second allowed energy states. Okay, now you can clearly see from this figure, this first and this considered second allowed energy state touch at some points, okay, with each other. Means there is no gap in these two states, so that we can consider that these are the part of valence band states. Now from above this level, we can clearly see from this figure there is some gap, so that we can say that okay, up to this level there is a valence band, and from this level onwards in higher energy states it is a conduction band. What is this? This is the simple plot of your energy eigenstates which show the periodicity in nature, and that periodicity will occurs through the wave vector K. Okay, that is the first thing. Okay, now this is your simple plot. So what you are seeing here, I am taking this one. See, then again same pattern. this pattern will again obtain here, then again obtain here, then again obtain here. Same way in left direction or negative k direction. Okay, so you are seeing here that this pattern is repeating after E in interval minus pi by a to pi by a. The same pattern you are able to draw whatever the obtaining in between minus pi by a region to pi by a region. Means this is your pattern you are getting in between minus pi by a region to pi by a region. The same pattern you are again getting pi by a to further 2 pi by a, then again 3 pi by a. So what is your periodicity? Period. What is the period? Period means after time interval or whatever your axis on that reference, what is the period? So the period is pi by a. Means after pi by a, the period is minus pi by a to minus pi by a to pi by a. The same pattern will be repeated. So the period will be pi by a minus minus pi by a. Then what you will get? Pi by a plus pi by a. It is 2 pi by a. So the period is 2 pi by a. So after every 2 pi by a, the same pattern will occur. So the period value is 2 pi by a. Okay. So see here also in the considered third allowed energy bands, again same thing is repeated, again repeated for next one. If this is your considered case, so then it is again repeated, again repeated, again repeated. So this is what? Your wave function. Your allowed energy state is what? Nothing but a wave function. In this allowed energy state, there is definitely one wave function psi. For this allowed energy state, obviously some wave function psi 2. For example, qualitatively. So what I am trying to say, this wave function is also have some periodicity. Now, whatever the property is here, whatever the property of wave function here, the same property is repeating again and again for each allowed energy state wave function. For each allowed energy state wave function. So, if you know the wave function in this region, this is known as your first Brillouin zone. So you can predict the wave function property or any property. Why? Because wave function have complete information about any quantum mechanical particle. So if you know the wave function in this region, then you can say that we know the wave function value in all the region, in all the extended region. Okay. So that's why this first Brillouin zone is important. So no need to worry about whatever the extended zone means here or here or here. If you know your wave function property in this considered zone, means first Brillouin zone, you can say that, okay, this is enough for me. On the basis of this value, whatever I am getting in this first Brillouin zone, I can able to draw the wave function for all considered region or in all available region. Okay. So that is first thing. So this is the complete diagram. This, whatever the picture plotted here, this is also known as a periodic zone scheme. Okay, periodic zone scheme. Periodic zone scheme. You solve the Schrodinger equation for one-dimensional arrangement of n atoms, real crystal structure system, where all the n atom are interacting with each other also, and then you modified the form of wave function, which can be which can be uh, which can be happen inside the crystal structure. Means whatever the wave function form inside the crystal structure, you try to predict. Who gave the assumption? Bloch try to give the wave function, form of the wave function inside the crystal structure. What he suggested? The wave function of any moving particle or electron will be like that. Means psi kr is equal to ukr e to the power I k dot r. And for this considered wave function, you solve the Schrodinger equation, and after solving the Schrodinger equation, what you will get? You will find that the allowed energy states having periodicity in k, and that allowed energy state is shown here in this plot, and that plot is known as a periodic zone scheme. One, this is second thing. One another interesting thing is what I already told. This is your band. In between these region, some allowed energy values are. Okay, this is your band. So this thing is known as bandwidth. Okay, now what is this? This is reduced zone scheme. When you only restrict yourself in this region, means pi by a region to plus pi by a region. So the same plot is here. Okay, so this is EK diagram. Okay, this is EK diagram, and this diagram restrict in a region in between minus pi by a to pi by a. EK diagram means E versus K curve. Okay, so this is your band. This is also your band. Now this is also your one band. See? So for optoelectronic application, this diagram is important. Why? Because if you know the property, or if you know the property of wave function, or simply wave function in this region, the same thing will be repeated again and again. Okay, after this region. Okay, so no need to worry about beyond this region, means minus pi by a to pi by a. You have to focus on only this region. Okay, so this type of plot is known as a reduced zone scheme. Reduced zone scheme means when you plot only the energy, when you plot the energy eigens, available energy eigen state in the region only minus pi by a to pi by a, then that type of plot is known as a reduced zone scheme. Now, again, this is not a reduced zone scheme. This is extended zone scheme. Whatever written here, it is wrong. It is extended zone scheme. So what is this? This is a plot for one energy eigenstates. So suppose this is your first energy eigenstate or first allowed energy eigenstates. So what is the extended zone scheme? What is the extended zone scheme? First you have to plot this, then whatever you are getting here, you have to plot for your next region. Then whatever you are getting here, again you have to plot for your next region. So extended zone scheme is nothing but the plot of one allowed energy state for different energy states, allowed energy states region. Okay. So this is also not a very helpful for governing the optoelectronic application. So what I will suggest that you have to focus on reduced zone scheme only. This thing also suggests some band gap value and all, but not more than that. So you have to focus on reduced zone scheme plot for governing the optoelectronic property. Reduced zone scheme, maybe, okay, I will try to again elaborate this. What I am telling, suppose this is your first allowed energy eigenstates or energy eigenvalues. Okay, so what? Then the second one will be also. Okay. Then similarly, the third one will be also. Okay. So what I am trying to say, forget about all these higher levels. Or if you take this level, so you have to choose only one level. Whatever, it's up to you. You have to take only one levels, and then for that level you have to draw the plot. Means in minus pi by a to pi by a region, if your plot is like that, and next it is like that. So for next band values, you have to plot this curve. Okay, you have to plot this curve. Okay, and similarly for third energy eigenstates region, allowed energy eigenstates region, third, whatever here you are getting, you have to plot this thing here. So this is your extended zone scheme. Okay, but it is also not very useful in governing the optoelectronic properties or for optoelectronic application. So whatever I already discussed, the same thing is written here. If we know the value of E and K, energy and wave vector K, lying within this period, then we know the value everywhere else because the periodicity. Okay, because the periodicity in nature of these values. Periodicity in nature of these values. Okay. So normally when we see the EK diagram, we look at the reduced zone picture. Reduced zone picture. If you see the reduced zone picture, and the highest field energy level is the valence band, and next one is the conduction band. Okay. What is the extended zone picture? In the extended zone picture, variation of only one level is shown in a particular period. So in extended zone picture, you show a discontinuity at plus minus pi by a. Plus minus pi by a. Here some discontinuity. Okay. Again discontinuity. Okay. Then plot the next band in next period and so on. So this thing already I discussed. Okay. So now why only focusing on top of valence band and bottom of conduction band? Now in reduced zone scheme, it is written in many optoelectronic devices text. What is this region? This is minus pi by a, this is pi by a. This is your bottom of conduction band, bottom, this point. And this point is known as top of valence band. So why only focusing top of valence band and bottom of conduction band? Generally for optoelectronic application or device application, in whatever you are getting in EK by EK diagram, you have to focus on only these 2 points. Why? There are two things. Free carriers, and second thing is available carriers are electron. Available electrons are number of electron, simply number of electron, and free carriers. So there are two things. So you will see that already I discussed how many electron will be for particular dimension of crystal structure. Okay. But generally it is found that the number of free carriers, remember this terminology, free number of electrons. Electron is also, it will be behave like a carrier, but in some particular case, means when that if any electron will be a part of outermost cell, then only there is a chance so that it will be behave like a carrier. But if you are talking about number of electrons, so whatever the electron present inside the crystal structure, you are talking about that electrons. Okay. So for optoelectronic application, it is found that number of free carriers or free carrier density is around 10 to the power 6 to 10 to the power minus 8 centimeter cube cc per centimeter cube. Okay. But this number is not enough, or very less than number of electron inside the any particular crystal structure. It will be order of 10 to the power 18 per centimeter cube. So the current will be flow by only free charge carriers. Okay, not for complete electron which are available inside the crystal structure. Okay. So generally, remember all this discussion. Now I am trying to plot again that EK diagram. Suppose this is your E axis, this is your K axis. Now I am plotting This is your conduction band. This is your valence band. So the probability or possibility for reaching the electron from valence band to conduction band is here more. Okay. From this point to this point is always more. So nearby this point only the free carriers will be accumulate. Okay. That's why we only focus on nearby top of valence band and bottom of conduction band. Okay. Nearby. Nearby means, suppose this is your bottom of conduction band, this is top of valence band. So this region. So obviously, if suppose here E value, then here E plus delta E value. Okay, here E value. Then here the energy value are E minus T. Okay. So nearby. So near to these points means near to top of valence band and near to bottom of conduction band. This band is nearly a parabola. Parabola. That's why we always take a approximation, parabolic approximation of band. Parabolic approximation of band, and we can calculate one term that is known as a effective mass of charge carrier. Effective mass of charge carrier means both electron and holes, electrons and holes. How? There is one formula, m star is equal to 1 upon h cross square divided 2e upon divided k2 inverse. Okay, so see here, what is this? This is the second order derivative of E curve with respect to K. Energy with respect to K points, wave vector. Okay. So how you will get this? Only how you will calculate this? Only if you consider this parabolic approximation near, very close to the top of valence band and bottom of conduction band. So why only focusing on top of valence band and bottom of conduction band? Because for calculating the effective mass of charge carriers, how you will calculate this effective mass of charge carrier? That is calculated by EK diagram in reduced zone scheme. Okay. So the same thing is written here. For this course on semiconductor optoelectronic, it is sufficient for us to see the reduced zone picture. More importantly, it is even sufficient for us to focus only at the top of valence band and bottom of conduction band. So why focus on? Due to getting the effective mass value of charge carriers. Okay. So when we calculate the density of a state, we will consider it in my next video lecture. So what is density of state? Available energy states per unit energy range. Okay, available energy states means in EK curve whatever the energy states available per unit energy range. Per unit energy range, how many states are available? That is simply known as a density of states. So when we calculate the density of state, okay, we will see that the density of state in a band is extremely large, but the carrier concentration which is responsible for flow of current is extremely small. Okay, what? So the same thing I already told. Carrier concentration which is responsible for flow of current is extremely small, but density of states means available state for all electrons are large. Okay, so the electrons are in the lowest portion of conduction band and the holes are close to the top of valence band, and they are the ones which participate in all optoelectronic process. Means what I already discussed here, whatever the available holes here, this is your valence band, this is your conduction band. So that will only means whatever the electron available here, that will only will shift to conduction band, then corresponding hole will be generated. So that will only take a part in conduction. That's why we should focus on only top of valence band and bottom of conduction band. Top of valence band, bottom of conduction band. This is your conduction band, this is your valence band. This is bottom of conduction band, this is top of valence band. Therefore, you rarely need to go till the end of Brillouin zone. Almost all practical devices utilize carriers which are close to the bottom of conduction band and close to the top of valence band. Means till the end of Brillouin zone. So what is Brillouin zone? Minus pi by a to plus pi by a. This is your K, this is your E. This is your conduction band, this is your valence band. So no need to reach till the end of zone boundary. You have to restrict yourself nearby the top of valence band and bottom of conduction band. Top of valence band and bottom of conduction band. And if you see a device oriented book, they will draw only the small part of the EK diagram. Okay, and let me see the relevant portion of EK diagram and discuss further. So this is your only the relevant portion of EK diagram for device application. This is what? In dotted line, zone boundary. This is minus pi by a. Okay. So what is the relevant diagram? Nothing but this only. One portion of conduction band which is in between the first Brillouin zone and one portion of valence band which is in between the first Brillouin zone region. Okay, so this is your bottom of conduction band, this is your top of valence band. So that is the relevant portion of any EK diagram only. for device application. Okay. So we know now EK diagram, and we will see that K values are discrete, but numbers of values are so large that you plot the continuous curve. Actually, we will see that this K values, whatever this K vector, also showing discreteness. Okay, means it is not a continuous, but they are so closely spaced so that you are getting a continuous numbers, then you are able to plot a continuous curve. So there are material in which the top of valence band coincide with the bottom of conduction band. These are called direct band semiconductor. Now I am discussing about two class of material which are having direct band gap and indirect band gap. So this is your what? Band gap, e.g. Now these band gap exist in a two-way in any semiconductors. What is the two-way? See here, this is your valence band. This now the conduction band lie here. Bottom of conduction band lie here. Okay. So what is this? This is indirect nature of band gap. Indirect nature of band gap. Why? Because this is your K point for corresponding top of valence band, and this is your K point corresponding bottom of conduction band. So these two considered K point are what? These 2 points are different, not same. So that type of band structure is known as a indirect nature of band gap or indirect band gap structure. Okay, such type of band structure is considered as a having indirect nature of band gap. Okay, why? Because the bottom of conduction band and top of valence band not existing on a same K point. Okay, now this is your top of valence band, this is your bottom of conduction band, and they are exactly existing on a same K point. So such type of material is known as direct band gap material, or such type of band gap is known as direct band gap. Okay. So the same thing is written here. There are material in which the top of valence band coincide with the bottom of conduction band. Then these are called the direct band gap semiconductor. Coincide means they are occurs at the same values of K. Now there are also material in which the top of valence band does not coincide. Top of valence band does not coincide with minima. Top of valence band does not coincide with the minima of conduction band. So these type of band structure are called as a indirect band gap semiconductor. The minima of conduction band EC and top of valence band is denoted by EV. Okay, so there are two notation also. EC is EC and EV. E suffix C, E suffix V. So this is bottom of conduction band, and this thing is known as a top top point, top of valence band. Okay. So K is the propagation. So now we are discussing about importance of EK diagram. Importance of EK diagram. So first how we will get the EK diagram, then which portion is relevant and why. Okay. So already we discussed, and some qualitative means indirect nature or direct nature. So direct nature band gap is always useful for optoelectronic application. Now K, what is K? K is the propagation vector of the electron wave function, whose magnitude is given by 2 pi by lambda. Magnitude is given by 2 pi by lambda, where lambda is de Broglie wavelength of the electron in semiconductor. This K is such that momentum P is given by H cross K. This momentum is very often called crystal momentum. Okay. What? When I introduce the quantum mechanics in that video lecture, I already suggested or given the formula which is proposed by Louis de Broglie. What he proposed, that any moving particle, the wave is associated, and that wave have a wavelength which value is lambda is equal to h upon p. Okay. So now p is what? If p is momentum, h upon lambda. If you multiply by 2 pi in numerator and also by 2 pi in denominator, what you get? You will get h upon 2 pi is what? H cross, and 2 pi by lambda means lambda upon 2 pi. It is what? K. 2 pi by K. So P is what? H cross K. Okay. So this term is referred as a crystal momentum. Means for any specimen, specimens means a small portion of your crystal structure, semiconductor crystal structure, which you are using for observation, for device application. Okay. So that is your specimen. So in term of wave vector K, the crystal momentum is what? H cross K. Okay. And the electron is responding to the external force as if it is a free particle. What I am trying to say? Suppose this is your specimen of any semiconductor, means there are still some charges, free charges. Okay. If there is no external electric field, simply a semiconductor specimen, there are some charges. So due to these charges, they have set up one internal electric field, EI. Okay. And now when you bias, when you arrange the terminal of this specimen with battery terminal, then the external field also applied. Okay. E external. E external. Inside, through the charges available inside the crystal, also producing one electric field that is known as an internal electric field, and its behavior is very complex. Very complex. Okay. But when you add the terminal of this specimen with battery terminal by any biasing, means you are applying one external electric field. That external field will be applicable, means they will try to move only a free charge carriers. Free charge carriers. Okay. and due to that free charge carriers only the crystal momentum, means by motion of that free charge carriers only that crystal momentum terms came. Okay, free charge carriers motion. So then it moves with an, so when the free charge carriers move, okay, charge carriers, then obviously it's have some velocity and also mass. Okay, so that mass is known as a, at that time when these free charge carriers are in motion, that time mass is known as a effective mass, and that effective mass value is given by the formula m is equal to 1 upon h cross square divided 2 e upon dk2 inverse. Okay, that I already given. Okay, so when momentum simply m into v, t is equal to what? M into v. So in that case, when free charge carriers is moving, that m is what? Nothing but effective mass, and motion of that motion of that free charge carriers particle will govern the crystal momentum. Okay, first thing. Now for device application, current value is important. Okay, so the current, drift current is what? NQ mu E. Okay, so N is what? Carrier concentration, Q is charge value, mu is mobility of charge carriers, and E is applied electric field. So mobility, E is what? How you will get a charge drift carrier drift current value? You will get by this formula. This formula contains the mobility term, and that mobility is again computed by this formula, means mu is equal to E tau upon m, where tau is carrier recombination time. Okay, and m is what? Effective mass. So by getting the current value, you have to know mobility, and by getting the mobility value, and means if you want to calculate the mobility of charge carrier, you have to know the effective mass of the electron. So how you will get the effective mass of electron? It will be calculated from EK diagram. Okay, so that is the importance of EK diagram. And even which portion of EK diagram? This portion in between minus pi by a to pi by a, means first Brillouin zone. Okay, so to summarize, for a given applied electric field, you need to know the mobility, which is depend on m star, means effective mass, and you need to know the carrier concentration n, which depends on the density of state, we will see later, and the probability occupation Fe, and to know the m star you need to know the EK diagram. That is the important thing. Okay, so thank you. I think it's enough for today's video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.